Hello, today we're going to be talking about rotational motion. In the past, a lot of our angles, we've used units of degrees, but no longer for rotational motion, we're going to be using radians the majority of the time. And if you do get given questions in degrees, you're probably going to want to convert to radians first in order to use your rotational motion kinematics equations that we're going to learn about today. So rotational motion, we're talking about circles and things that move around an axis. And so when we talk about moving around an axis, our motion is going to be in terms of the degrees of rotation, or theta. This will create an arc length if it is a circle of S, and this helps us convert back and forth between tangential motion and rotational motion. So we're going to talk more about this next week, but I did want to point out, so if we have our arc length of S, and we want to get to our rotational displacement of theta, then we can consider that our circumference is 2 pi r, if this is r here. I think that's not a shock to anybody. And if we wanted to find that arc length S, we could use ratios. So I have an arc length of S out of 2 pi r total circumference must be equal to theta is our degree of displacement over 2 pi total radians in a circle. So we know there's 2 pi radians per circle. And if we want to take a fraction of that, that's going to be theta out of 2 pi radians. And so we can see these 2's cancel, the pi's cancel. If I cross multiply my r, my arc length S is going to be theta times the radius. So this is a really useful way to transfer back and forth between tangential motion and angular motion. Again, we will talk about this more next week. The key to this is this theta must be in radians for that ratio up there to have worked. And it's often left unitless. And so because people don't like writing rad. So if you see it unitless, in this case, that is okay. But be aware that it is in radians unless otherwise specified. Okay. So what are we going to do with this? Well, we can use this to look at rotational motion. So we know when we're talking about translational motion, we have x, or delta x is our displacement. And I just said over there, delta x, when we're talking about angular motion, we can transcribe that into change in the angle. And in linear motion, we have velocity is the change in position over time. And so that gets transcribed to omega is equal to change in the angle over time. And that's going to have units of radians per second or inverse seconds if you get tired of writing rad. And this is the angular velocity. All right. Okay, so what about our next thing? Let's do the acceleration. That was the next thing we learned about in our class, so let's do that again. So angular acceleration is change in velocity over time. So if we're going to talk about this in radial motion, we have alpha. Alpha is our angular acceleration, and that is going to be the change in our angular velocity over time. That will have units of radians per second squared, or s to the negative 2. Okay. What did we do next in this class? So that was basically our intro to motion, and then next in this class we did kinematics equations. So it turns out that our kinematic equations can also translate to rotational motion. So we had 4 kinematic equations this year. We had V equals VI plus AT. We had delta X is 1/2 AT squared plus VIT. We had have V final squared is V initial squared plus 2A delta X. And we had change in position is the average velocity times time. So these can each be translated into rotational motion equations. So for instance, this first one, we're just going to replace those velocities with omega. Omega equals omega initial plus AT. And for this next one, we know alpha t. Gotta make sure I translate everything, right? So we have omega is omega initial plus alpha t. For this next one, we're going to have the change in angle. It's going to be 1/2 alpha t squared plus omega initial times t. And I want you to see, could you translate these next two? I will write these in after I'm done with the lecture, so you can check back here on the notes. Let's see if you can translate those next two equations. All right, so all of these translations can actually also be derived. And to derive them, all you need to know is that we can translate between rotational variables and linear variables. So we started over here. We have that S is theta R. You could also find that VT is going to be, we know that's R omega. And that is going to be the S arc length over T. And so you can use that to translate our velocities into omegas. And then we know that acceleration, tangential acceleration, is the change in velocity over time. So that's going to be Vt final minus Vt initial over time. And that's going to be R omega final minus R omega initial over time. That's going to be R alpha. We can see there, if we pull out these R's to the front, we end up with R and then change in omega over time, so that's R alpha. So if you would like to, instead of just translating, you could derive each of these rotational kinematic equations from the linear ones using these conversion factors. Okay. As a side note, we also remember from our centripetal acceleration is Vt squared tangential squared over R, and we derived that in that unit. That's the same thing as R omega squared. So every once in a while that comes up as well. Okay, so that's our translation of kinematics. Now, technically, this rotational kinematics could apply around 3 different axes. So it could be rotating around its x-axis, its y-axis, and its z-axis all simultaneously. But for this class, for AP1, you're only ever going to be asked to analyze it around one axis. So in kinematics, we did have 2D for linear, but for rotational, you only have to worry about that one-dimensional rotation around one axis. Also, as a note, we talked about this in class, but our omega follows the right-hand rule. And so that means clockwise is negative, and counterclockwise will be positive. So that's from that right-hand rule. Okay. All right. Moving along. We can make more analogies from this class. After we did kinematics, what was our next unit? Let's see. We did some dynamics with Newton's laws, right? So we said we had F net equals the sum of the masses times acceleration for an object. And we know from our first pivot that F net translates into torque net. And so torque net is going to be something times alpha. What's going to go here? Well, what we know is that mass was a measurement inertia. So what goes here must be a measurement of rotational inertia. And so we call that actually the moment of inertia. And that's represented with an I for moment of inertia. All right. So this I value, if we were to look at the units, we could see that torque, actually we'll come back to that I, we know that torque is in units of Newton meters, newtons times meters. Now, because this was the force times the radius, right? I don't know why my pen's a little jittery. So the force times the radius times sine theta, so we get those perpendicular angles, we know that, will give us the torque. Now, interestingly, these technically are the same units as joules, but you do not call them joules, all right? So when you're talking about torque, it is not the same thing as joules. When you're talking about torque, use newtons times meters to let everyone know you're not talking about energy, you're talking about torque. All right, so we have newtons times meters is our units for torque, and that's equal to something times seconds. Ooh, come on, pen. Seconds to the -1. All right, so we know, oh, sorry, -2. My pen not working is throwing me off. Seconds to the -2, right? So the next question is, what goes here? Well, newtons over here we know are kilograms, meters per second squared times meters. That's equal to something 1/second squared. So those go away. So then my units for moment of inertia must be kilograms meters squared. And it turns out that moment of inertia is calculated as the sum of all masses times the radius from the axis of rotation squared. So that's mr squared. Now, this is sort of one of those integral calculus things you'll do in APC next year for different shapes. But for now, for AP1, just know that this is going to be different for different shapes. So in a hoop, all of that mass is located at the outer edge. So for a hoop, it really is just mr squared. But what if you have a disk? So some of the mass is like right next to the axis of rotation, very little r, and some of the mass is further out. That means our moment of inertia is going to be smaller because the part closer to the axis has a smaller radius multiplier. So you end up with mr of the disk squared, but 1/2. Because some of that mass is not as hard to move because it's closer to that axis. If you have a solid sphere, for example, you're going to have 2/5 mr squared, and then for a hollow sphere, you're going to have 2/3 mr squared. Don't worry about memorizing this. If it's not on your equation reference sheet, they'll give it to you in the problem. The only one I would maybe just make sure to have on hand is that hoop. They do sometimes expect that. All right. Okay, so that is our comparison to Newton's second law there. Torque is I alpha. Moving on, what did we cover after Newton's second law? Well, after Newton's second law, we did energy. So these, we now need to worry about the motion, rotational motion. I know some of you brought it up during that unit, so now we're going to talk about it. So we said before that total mechanical energy is going to be Eg plus E spring plus Ek. But now what we're going to see is that Ek comes in two flavors. I mean, it comes in more if you consider thermal and stuff, but for now, for mechanical energy, we're going to have Ek translational, and we're going to have Ek rotational. Come on, pen. That we have to add together for that total kinetic energy. which means our energy equation now is going to be mgh plus 1/2 kx squared plus 1/2 mv squared. And now we need that rotational energy too, which turns out you can translate it just like all the others. It's going to be 1/2 I omega squared. So you might need to find that at some point. We also learned that work was force times distance. Again, this translates, so work rotational is going to be torque times the angle. So instead of force times distance, we have torque times the angle. Continuing down. I know I'm running out of colors. Should we go orange? Then our next unit we just finished was momentum. And once again, in momentum, we had P. Momentum is mass times velocity, or P equals mv. And we can translate that into L, because we've really run out of letters now. L is going to be angular momentum. Momentum is equal to I omega. Come on. And we had our impulse was J equals F net times time. And so now we have the change in linear or rotational angular momentum. We even ran out of letters, so now we just use delta L is equal to torque net times the time that's applied. So we see that that translates as well. All right. So you can see that with this unit, we are basically going to be working on figuring out if we need to translate things from linear to rotational. The rotational problem solving is very similar to how it was in linear, but we might need to transfer back and forth. And the other thing is to remember that the way we get between kinematics and dynamics is usually through acceleration. So often what you're going to be looking for is to solve for alpha, either through dynamics or kinematics, and then use that to transfer to the other one. So alpha is our shared variable between kinematics and dynamics. So do remember that when you're looking to solve problems. All right, thank you. Have a good day.